Up quark. If you strip ordinary matter down to its absolute core, one of the first particles you encounter is the up quark. It carries a positive electric charge equal to 2/3 of a proton's charge, and it sits inside both protons and neutrons, bound tightly by one of the four fundamental forces of nature, the strong nuclear force. Every proton contains two up quarks and one down quark, while every neutron contains one up quark and two down quarks. That small numerical difference is enough to determine whether a particle carries a net positive charge or none at all, which in turn shapes the identity of every atom in the universe. Now, here is something that surprises most people. The up quark is almost unimaginably small and light, with a mass so tiny that it contributes almost nothing to the mass of the proton it lives inside. In fact, if you add up the masses of the three quarks inside a proton, you only account for about 1% of the proton's total mass. The other 99% comes from the energy of the gluons constantly flying between the quarks, binding them together. That means nearly all the mass of your body, your chair, this planet, is really just frozen energy from a force holding tiny particles in place. The up quark was proposed in the 1960s by physicists Murray Gell-Mann and George Zweig working independently, and it became one of the foundational pieces in a sweeping new framework called the Quark model, which reorganized our entire understanding of the hidden structure of matter. Down quark. The down quark works alongside the up quark, but it carries a negative electric charge equal to 1/3 of a proton's charge. Inside a proton, one down quark joins two up quarks. Inside a neutron, two down quarks join one up quark. That single swap is enough to completely change the particle's identity, its charge, and how it behaves inside an atomic nucleus. Down quarks are slightly heavier than up quarks, which is actually part of why neutrons are heavier than protons, and that mass difference has enormous consequences. Because neutrons are heavier, an isolated neutron outside a nucleus is unstable. It decays in about 10 minutes, transforming into a proton, an electron, and a ghostly particle called an antineutrino. That process, called beta decay, is one of the most important reactions in nuclear physics, and at its heart, what is really happening is a down quark changing into an up quark. The entire transformation of an atom, the release of radiation, the chain of events that make certain elements unstable, all of it traces back to that one quiet change happening inside the nucleus. Down quarks are part of the reason stable matter can exist at all, and they are also part of the reason the universe is dynamic, changing, and full of nuclear processes that have powered stars for billions of years. Charm quark. Charm quarks are heavier, rarer cousins of the up quark, and they do not appear anywhere in the ordinary matter around you. To find them, you need extreme conditions, powerful particle accelerator collisions, or the violent impacts of cosmic rays arriving from deep space. Their discovery in 1974 was one of the most dramatic moments in the history of particle physics. Two independent research teams, one at Stanford and one at Brookhaven, found evidence for the same new particle at the same time from completely different experiments. It was so unexpected that the scientific community called it the November Revolution. The particle they found, called the J/Psi, was made of a charm quark and its antimatter partner bound together. This discovery confirmed that quarks came in pairs and followed a deeper symmetry than anyone had fully appreciated. It also validated a prediction that had been sitting quietly in the theoretical literature, largely ignored, for 2 years. What is also remarkable is the scale of the charm quark's existence. It weighs roughly 2,500 times more than an electron, yet it vanishes from existence in less than a trillionth of a second. In the incredibly brief moment it exists, it can barely travel a distance smaller than an atomic nucleus before transforming into something else. Strange quark. Strange quarks earned their name because particles containing them behaved in unexpectedly unusual ways when they were first discovered in cosmic ray experiments in the late 1940s and 1950s. Physicists watching cloud chambers noticed particles that seemed to be created rapidly in high-energy collisions, but then decayed far more slowly than the physics of the time could explain. They called this behavior strangeness, and the name stuck even after the underlying explanation was found. The resolution was that strange quarks can only be created in pairs during the strong nuclear force interactions that make them, but they decay individually through the much weaker weak nuclear force. Strange quarks carry the same electric charge as down quarks, but they are roughly 100 times more massive, placing them in a heavier generation entirely. Top quark. The top quark is the heaviest fundamental particle ever discovered, and by a remarkable margin. Its mass is roughly equal to that of an entire gold atom, which is extraordinary for something considered a structureless point particle. To put that in perspective, the top quark is about 340 times heavier than the up quark, and nearly 40 times heavier than the bottom quark it's paired with. Because of this enormous mass, the top quark decays almost instantly after being created, disappearing in roughly 500 times 10 to the power of -25 seconds, which is about 100 times faster than the strong nuclear force can even bind quarks together. That means the top quark is the only quark that never forms a bound state with other quarks. It decays before that process can even begin, making it uniquely visible in ways that other quarks are not. Scientists at Fermilab finally detected it in 1995 after a search that had taken nearly 20 years since its existence was first predicted. The discovery required colliding protons and antiprotons at enormous energies. Because the top quark's mass is so large, its properties are deeply connected to the Higgs boson, the particle responsible for giving mass to other fundamental particles. Bottom quark. Bottom quarks are heavy particles from the same generation as the top quark, though they survive long enough to be studied in much more detail. They were discovered in 1977 at Fermilab when a team led by Leon Lederman found a new particle called the upsilon, which was made of a bottom quark and its antimatter partner. Bottom quarks carry the same electric charge as down and strange quarks, but their greater mass, about 4 to 5 times heavier than a charm quark. Dedicated experiments, including the Babar experiment at Stanford and the Bell experiment in Japan, were built almost entirely around studying bottom quarks and their antimatter partners to measure this asymmetry with extraordinary precision. Every time a bottom quark decays and scientists measure exactly how it transforms, they are reading a message encoded in the fabric of the universe, a message about why anything exists at all, and what rules were written into nature from the very first moments of time.